Hi, I'm Hyunji Kim at Postec, and this talk is about natural language SQL, Where Are We Today, which focuses on the evaluation of existing methods for natural language SQL. The datasets and source codes of this paper are published on the GitHub site below. Natural language SQL, and SQL in short, is to find a SQL statement to answer a natural language question on a given relational database. For example, if a question, how large is Texas, is given on the geography database, we can translate the question to the following SQL query, then we can answer to the question. SQL has been studied both in the database community and the natural language community since the 1970s. Early techniques are rule-based methods that use mappings and translation rules. And recently, many studies have been conducted by using the state-of-the-art deep learning models and algorithms. However, comparison among the existing methods has not been performed properly. All of the recent studies only compare to a limited set of previous methods. And furthermore, they evaluate their performance using only a subset of existing benchmarks. A more serious problem in the previous studies is that all accuracy measures which they use are misleading. Let me introduce the second problem in more detail. In the following example, how can you evaluate the correctness of the translated SQL query? At this time, we assume that a correct SQL query is given. You can evaluate the correctness of the translation by comparing two SQL queries. Except for some papers based on user studies, all previous work measures accuracy in the manner described before. And here, there are three ways to compare two SQL queries using existing measures: string matching, partial matching, and result matching. However, all three of these existing methods might cause errors in measuring accuracy. First of all, using string matching, two equivalent queries can be judged as different queries for regions such as different alliances, different orders of conditions in the web clause. And partial matching has a similar problem with string matching since it uses syntactic information only. For example, two same join queries can be judged as different if one is nested and another is flattened. Result matching, which is compare execution results of two SQL queries to different queries, can be judged as the same query when they have the same execution result by chance. This paper solves the two issues mentioned before, and our contributions are as follows. First, we present a comprehensive survey and a general taxonomy for SQL. And second, we evaluate 11 state-of-the-art methods by using 14 benchmarks. And third, in order to accurately evaluate existing methods, we propose a practical tool for measuring accuracy. And finally, we provide important findings from extensive experiments. All benchmarks and our validation tool are available on our website. This website also presents a challenge to the newly collected benchmark WTQ. You can join us by submitting your program according to the given instruction, and we will measure the performance of your method on WTQ. Now we introduce recent methods for SQL. In the paper, we present 16 techniques in the last 5 years. The existing methods have the following architecture in common, and we propose a general taxonomy for each step to classify the techniques. First, they take a natural language question and a database as input. For natural language question, there are 4 classes using different natural language preprocessing techniques. And for database D, we show domain adaptability constraints and database utilization. Some methods require new training data or new dictionaries to process new databases. Some assume that database D consists of a single table only. And some methods use only the database schema, and some use both the schema and values. And some of the methods use additional inputs such as open domain knowledge bases. And they go through 3 steps called input enrichment, translation, and post-translation. Deep learning-based methods also have a training phase for training their deep learning models. Before the translation, some methods try to obtain or remove information about databases. There are 3 input enrichment techniques: tagging, linking, and anonymizing. Tagging is to attach text to a dimension in the question. Linking is a technique that links words or phrases in a natural language question to schema entities. Anonymizing is to find references to data values in natural language question and then replaces them with a special indicator. Techniques are further divided into enrichment for database schema and values. For example, ILL attaches tags to both int, forages, and schema entities. LSP performs anonymization. For translation techniques, reducing methods can be divided into deep learning-based and rule-based. Each deep learning-based method treats the database schema as either a part of the auth vocabulary or the input. The former puts a table or column names into the auth vocabulary and decodes schema entities by selecting words from the vocabulary. In contrast, the latter takes the database schema as input and decodes schema entities by copying from the input. And rule-based methods are divided according to whether database is used directly or ontology is used. And translation techniques can be further divided according to the input and output of the model or algorithm that generates SQL queries. For example, LSP puts the anonymized question into a deep learning model as an input sequence. At this time, LSP uses an encoded code model that takes the natural language question as an input sequence and generates a SQL statement as an output sequence. Unlike LSP that only uses the question as input, ILL uses both the question and the database schema as inputs of a deep learning model. The model generates a simplified derivation tree rather than a sequence of SQL tokens. Now, each technique goes through the post-translation phase to complete the SQL query. And finally, they output the SQL query. For output, the supported SQL syntax of every method is limited, so we indicate which design choice leads to the restriction. Now present the experimental results. First, we use 14 benchmarks, including a really valid benchmark WTQ. In order to properly measure the translation accuracy, we need to determine the semantic equivalence of two queries, rather than syntactic equivalence or result equivalence. If two queries output the same result for an arbitrary database instance, we call that these queries are semantically equivalent. Although some previous researchers propose automatic tools, it cannot support most of the SQL queries we use because of their limited SQL coverage. Since expensive manual validation is required for such queries, it is important to increase the coverage of the automatic validation. To solve the problem, we use database techniques such as query rewriting and database testing, and propose a validation tool of multi-step complementary filters. Our validation tool has 4 filters and achieved to cover 97% of total test queries, while the state-of-the-art tool Cosette covered only 16% of those queries. I will show the results. The figure shows the results using simple queries, which is on single table with single column collection, aggregation, and selection. In this experiment, ILS shows variable accuracy in WTQ and SQL. And surprisingly, even the queries are simple, the highest score on WTQ is only 44%, and most are less than 25%. The reason is that the column names and questions in WTQ varies a lot. Please refer to our paper for details. Next, we conduct experiments using complex queries. The figure shows the result of deep learning techniques. 5 of 9 deep learning techniques are excluded because they can only support simple queries. First, the overall accuracy has dropped compared to the case using simple queries. Surprisingly, the oldest deep learning-based method, MSP, shows the best accuracy on both single-domain datasets. However, it shows nearly zero accuracy on cross-domain datasets. This is our summarized result. As shown in previous results, there was no clear winner among 11 techniques. And also, there were many issues to solve, such as cross-domain support and accuracy drop on small training datasets. To conclude, we present a comprehensive survey and perform thorough performance evaluations of cutting-edge analytical techniques. We give important findings and insights for future research. We also note the critical problem of previous studies that use misleading measures. You can find our benchmark on the following detailed site. Thank you for listening to my presentation.